Again, welcome to, I think we are in week 7 now, and we are midway to where we're supposed to be. So that's exactly where we need to be, I guess. And also, we're starting a new topic today. But before I do that, I just want to remind you again about the exam that is coming this Tuesday, and that the review is actually on Canvas. So hopefully that you already have come up with a plan to tackle it. And that's probably the way to do it because it's a lot of problems that you have to go through. So make sure you have them all systematically reviewed and basically understand them. Send me a message if you have difficulty with them or something, and I'll be more than happy to open a session just for the review discussion session so that, or you can open it yourself actually and see if you have people who can work with you on these things. And it's a good idea to work together on these things. So that's basically in terms of the exam. Again, the exam is on Tuesday. It starts from 4 o'clock in the afternoon, which means that there is no class on Tuesday because you're supposed to be doing your exam. Some of you will start right away on it and will end by the end of the night, basically, I think 11 p.m. And I'm hoping that you guys will go through it. Now, here is the idea. The exam is actually timed. It doesn't mean that you have the entire period of time where you're going to submit the exam. You only have an hour and a half or so, an hour and 25 minutes to be specific. So that means that once you start it, you cannot decide to take a break and come back to it. Canvas will submit it on your behalf. So make sure that you have everything done before you start it. I'm sorry. You have your water, excuse me. You have your water, you have your coffee, you have everything. No, I will not. Okay. If you have any questions, V is asking about the answer key for this ones. I was not planning on doing it, but if you guys have any questions, please let me know in terms of the review. Okay. Uh, no, you don't have to turn in the review, Vanessa. Okay, the review is for your own thing. It's not graded, actually. The only thing that I wanted to make sure is that you guys check that you did the review, okay? Because you're aware of it and you're preparing the exam based on it, okay? So again, I'm hoping that you guys spend enough time on it. Usually, you need at least 2 hours to go through everything, okay? That is if you don't have any questions or difficulty with one or more of them. If you do, please let me know so that we can basically work them together or answer your question or something like that. I will not answer anything past noon on the day of the exam because at that point, that's it. Basically, you're on your own. So you have to really start working on it and making sure that you're ready for it. Again, 4 o'clock on Tuesday, October 13th, and ends at 11 p.m. October 13th. Uh, you only have an hour and 25 minutes to do the actual exam. Once you start it, you cannot, for some reason, stop it because Canvas will basically submit it on your behalf. So make sure that you are well rested before, you are focused, and so on and so forth. If you are the type of person who works better during the night, you might start it later. If you are a person who is probably works better during daytime and sleeps early like myself, you probably need to start at 4 o'clock. So that's your prerogative, and I'm hoping that you guys have that in mind. Uh, Again, no class on Tuesday. The class will resume on Thursday, a week from today. And that's basically, in a nutshell, all I want to talk about in terms of the exam. Okay. Uh, we're starting today a brand new topic, namely the branch of thermodynamics. This is another branch of physics that we need to focus on. And it's going to be part of the next exam, the last exam that we have for this class. So if you guys don't have any questions, let's get into the these topics. So the science of thermodynamics is kind of weird science, okay? First of all, it touches upon every single branch of science out there, uses thermodynamics. So the science itself is called thermodynamics, okay? or how heat is exchanged. Thermo, that's an E, dynamics. And it was discovered really, or at least it was put, it was started by an engineer, not even a scientist. In the early 1800s, I think around 1824, Mr. Carnot was an engineer for the French army working in the railroad at that time. Sadi Carnot, his name. He wanted to, a simple question. He asked only a simple question. His name spelled Carnot. Okay. He wanted to know what is the most efficient engine. That's a simple question. It's as simple as it can get. He works as an engineer. He works for the railroad. At that time, the heat engine for the railroad, basically for the trains, was something that he was working on it day in day out. He knows what to do. He has a boiler basically in the engine at that time, made out of water, and they go and bring wood and they put it under the boat to boil more and more water. And as the steam comes out, it turns those pistons, and the pistons turn and basically makes the wheel going, and the engine moves, and with it drags all of the cars behind it, and that's basically how trains work. Okay. So he wanted to know what is the most efficient engine. What he did actually, he said, okay, allow me this, grant me this. And what is that? He said, grant me that heat cannot move from a cold source to a hot source on its own, spontaneously, without any intervention. Heat, without any intervention, is supposed to flow from a hot source to a cold source. So there is no process in nature that allows for heat to spontaneously move from a cold source to a hot source, so that the cold becomes colder and the hot becomes hotter. This is not possible. So if you grant me this, because this is a daily observation, then I will show you what the most efficient engine is. And indeed, he answered that question. Remember, that was 1824. In doing so, he came up with the most efficient engine. Until today, nobody can beat Mr. Carnot's engine. It is the best engine that can ever be. The most efficient engine, I should say. I mean, is it made out of, how about if we change water and put instead of it alcohol, for example, or put a different liquid in there? How about, for example, if we change the temperature to here and there? So that was all kinds of options that you need to think about. How to make the boiler, for example, bigger or smaller? Would that make it a more efficient engine? Would we, instead of using wood, for example, can we use different material to burn? So there are all kinds of things. But in doing so, he ended up with an answer to the question. People realized that he was onto something, okay? And this law later on, which became the law, one of the laws of thermodynamics, people realize that this is not really a fundamental law. There is something wrong with this thing. There is a more basic law than this. And the law that they realized was the law of conservation of energy. So the energy is conserved first, and then we go talk about heat not spontaneously moving from a cold source to a hot source. So they reordered the laws, and they called the law that was discovered first, they called it the second law. Namely, this is the law that he discovered, although it was discovered first. And then the second law that they needed to postulate was basically classified as the first law. So basically, the second law is the law that I was talking about in terms of heat not spontaneously able to move from a cold source to a hot source. And the law that came after it, that was discovered second, was promoted basically to being the first law, because that's a more basic law. Namely, the conservation of energy is more fundamental than this one. So now we have two laws. sitting beautifully. And people were starting talking, okay, the first law of thermodynamics is the conservation of energy, and the second law is that of basically heat not being able to move spontaneously to from a cold source to a hot source. And everybody was happy, and the discussion was going on here and there, and things were going, I mean, all over the place. Great. Then people started to think that there is something wrong with this whole thing, that we actually needed how, because they talk temperature and temperature and temperature, but they had no way of coming up with a consensus of what is the measurement for temperature. So they needed actually another law before the first law. So they needed a third law, but that third law really have to go before the first. It cannot be between the first and the second, because it's supposed to be more basic than even the conservation of energy. Okay, because we have to first of all agree what temperature is before we start talking about heat and its exchange, and whether heat can spontaneously move from a cold source, which has to do with its temperature, to a hot source, which has to do with its temperature. So they needed a law that is more fundamental. So now they were faced with two options. We need to bump the first law that was discovered, and we called it second, to being actually third. And we need to move the second law that we discovered, which we called it first, to being the second law. And now bring the third law that we discovered last, basically the last law, and move it as the first law. Instead, since it was already popular and the naming there at that time, first law and second law, they were known. What they did is, instead of calling the more fundamental law basically any other thing, they called it the zeroth law of thermodynamics. So the trouble with this whole science, it was discovered backward. We discovered the second law first, and we discovered the first law second, and we discovered the zeroth law third. Completely in the reverse order of how things were supposed to go. Okay. The problem with this science, as I said before, it has applications everywhere that you can think of. It has applications in, first of all, physics, of course. We cannot do any energy. We cannot understand, for example, how energy is exchanged and heat engines and the principles behind it. They are supposed to be physics, because it has to do with temperatures in the room we are in, and all of these things. So physics relies on has connections, deep connections with thermodynamics, and need to basically be part of physics as a branch. Chemistry also relies on it. You do a chemical reaction. Is this chemical reaction even possible? Thermodynamics will tell you if that chemical reaction is even possible, or you need to inject in it something to make it happen. And when it happens, would it release heat, and how much heat is released? Since it's heat, you're talking about thermodynamics. Biology relies on it. No living organism, all living organism, they first of all dispense of energy, exchange energy, heat is involved all the time. Actually, the inside of the biology of any kind of living creature, whether plants or animals, there is all kinds of chemical reactions that rely on the principles of thermodynamics to see if it's even possible for it to happen, to process. Economy, I mean, engineering, of course, every single thing involves heat and exchange of heat and all kinds of things. So applications in daily lives everywhere. The trouble with this is it went even a step beyond that. The second law is also the law of order and disorder. There is a connection between that and the law of order and disorder, and this concept of entropy. Everything in the universe, for example, especially in terms of the black hole, when we talk about as being a singularity, and we talked about that when we were talking about gravity, everything is fine with it. The only trouble with it was the second law. Is the second law violated in there? It took the genius of Hawking's and other physicists to really calculate it, and they say that the black hole does not violate the second law of thermodynamics, because nothing should. To the point that today, philosophers and theologians, they are talking about the second law to prove or don't or prove the existence or non-existence of God himself. So basically, just to tell you how powerful this stuff is, that philosophy, religion, engineering, chemistry, biology, physics, everything is all in this branch of physics. So it's a very important topic. It is extremely important. And the second law, which is really, like I said, the beginning of everything, sits at the heart of everything. Whether a chemical reaction will happen or not depends on basically whether the second law will allow it. And if it doesn't allow it, how can you make it so that the second law will allow it? That's basically what we're talking about. So it's big stuff. It's huge things, okay? It's a lot of things in here. Okay, let's talk about the topics of today that we're going to cover in this one in here. Of course, the concept of temperature, and as I said in here, it's related directly to the zeroth law of thermodynamics. So that you know, here is what the zeroth law says. Let's say system A. It doesn't matter what that is, okay? And system B, doesn't matter what that is. They are in thermal equilibrium. What I mean by that is I keep them in touch with one another, okay? They're in contact with one another. And I wait a long time so that both of them feel the same. Both of them have the same temperature. They are in equilibrium. In other words, if this was hotter, if A was hotter than B, I will notice that heat will start flowing this way until both of them will reach equilibrium. At that point, the heat slows down, and there is no more heat. There is nothing, okay? If you like, if this was hotter, I put a food coloring on it, red, for example, and then I put this one blue, okay? And I will notice the red particles are moving with the heat in here, trying to equilibrium these things. And at some point, they both come to equilibrium, and there is no motion. The fluid is not moving anymore, and the heat is not actually exchanged. As a matter of fact, I can prevent the heat from moving. I mean, the particles from moving. I can only allow heat to be exchanged, and they will become in thermal equilibrium. So the point in here is they're in contact. Like, for example, when you take your cup of coffee from the coffee machine, it's super hot. And the room is normal. That's where you're sitting. Put your cup on the table and wait for it. Wait an hour, 2 hours, 3 hours, and look at what happened to the cup of water, cup of coffee. Taste it. It tastes like just the environment in it. So at that point, the cup of coffee and the environment, the air, have reached thermal equilibrium. They both have the same temperature. You take an extremely cold cup of water, for example, and put ice in it, and you put it on the table, and you come an hour, 2 hours, doesn't matter. Just wait long enough for it. First of all, the ice will melt, and second, the water will taste exactly room temperature. Okay? So at that point, they have reached thermal equilibrium. So what I'm saying in here is, given system A and system B, think about it, coffee and air, okay? They are in thermal equilibrium. Then if I do something else, if I take, for example, system C, which is something else, okay? Like, for example, the spoon next to both of them, like in the air, I think, and next to the coffee. And that too is in thermal equilibrium with system A. Well, the zeroth law says that A and C are also in thermal equilibrium. What this allowed me to do is immediately allowed me to invent thermometer. I can measure temperatures now. Take, for example, a cup of water, frozen, and put in it a device and start seeing its temperature rising as I put it under the boiler. And as it rises, it gains more and more temperature. I'm going to scale this device. So remember, now I have a thermometer, which is a device to measure temperature, and I have water. Okay. And then as it moves up, I'm scaling this. I'm saying, okay, this is the temperature of freezing. And this is the temperature when it boils. If I divide this denomination to 100, then I have invented the Celsius system. If I divide them to 180 and starting from 32 instead of 0, then I notice that it's going to boil at 212 degrees, and that's the Fahrenheit. So that's the scale. So this allowed me. Then, if I take my thermometer now and put it against something else that is not necessarily the substance I started with, and read the reading of the thermometer, that is how thermometers work. That is allowed to us by the zeroth law of thermodynamics. So the zeroth law of thermodynamics immediately allows us to measure temperature. Instead of saying This is cold, this is hot. And then I bring a thing, something else. Oh, this is actually cold than the cold one, the first one that I started with. So this is colder, this is cold, this is hot. Then I bring a fourth substance in here, and I say, okay, how about this one? Oh, this is hotter than the cold one, but less hot than the hotter one. But it's actually, and now I don't know. You understand? I don't know how. What is the difference between this one and that one? I don't have a number. It is not physics. It is not science, as a matter of fact, physical science, unless you append a number to it. This device now allows me to append a number to it. Measure the temperature of this first one, for example, I find it 47 degrees. Not only it's hot, but I know exactly how much it's hot, 47 degrees centigrade. Measure the temperature of this substance, for example, I measure it and I find it 32 degrees, doesn't matter what the scale is, centigrade. I measure the temperature of this substance, for example, I find it 12 degrees centigrade. Measure the temperature of the other one, it's actually 33 degrees. So it's only 1 degree above the other one. So there is a big gap between that and the first one. So now I have appended numbers to it, and I know exactly what the temperature is. So the zeroth law allows us to do that. I can feel, but feeling by itself is not good enough. So I really need the numbers, okay? And that is what the zeroth law of thermodynamics does for us. Then, of course, the concept of heat. And from the get-go, and this is the point in here for today, one of the questions, heat and temperature are not the same. Okay? Heat is an energy, and it's associated between an exchange between two systems. For example, when I brought my coffee from the coffee machine and I put it on the table, it has a temperature which is probably higher than that of the room that I am in. So what happened in this case, heat was exchanged from the coffee to the environment in this case, which is the room. The only reason why I did not feel hotter in the room is because the room is big. So its temperature has increased, as a matter of fact, slightly, but not to the point that I notice it because the room is big. Actually, I heated the entire house. I heated the entire town with that cup of coffee. But I would not notice it because it's really a very small increase because it's big. But the cup of coffee in this case, it lost some of its heat, some of its temperature in the form of heat. So the heat was actually left. So its energy actually is less now. It has less energy inside. Okay. Did I say less? I'm sorry. It's more. Okay, because it gets warmer. Okay. It actually has more energy in it because it was cooler to begin with. Now it's hotter. Okay. So that's basically the concept that I want you to understand. That is related to something else. Temperature is related to the internal energy of the substance. Okay. How much internal energy I have. And it can lose it in the form of heat. So that the substance basically now has less energy. Oh, I'm sorry. I'm giving you the whole thing backward. I'm sorry. I'm sorry. Oh, no. That's correct. I'm sorry. We're talking about the cup of coffee. So it is still good. We're still good. I'm sorry. So the cup of coffee has a lot of heat, a lot of internal energy in it. So it lost heat to the environment. So that's correct. There's nothing wrong with it. Because I'm thinking in terms of my cup of water in here next to me, which has a lot of ice in it. So it's actually getting heat from the inside, from the room I am sitting in, back into my water. And after a while, my water has less. So right now it has less energy, but it's receiving heat from the environment. So it's going to have its energy, internal energy higher and higher, meaning its temperature will go higher and higher. So you have to specify. So for coffee, for example, that is steaming hot, after a while, if I wait for it, it's going to be less heat coming from it. So in this case, it's lost some of the energy that it has, and now it has less energy in it, and it's colder now. Okay. For my water, it's the other way around. That has ice in it. It's the opposite. It has less energy to begin with, and now it's receiving heat from the environment, and that heat will make it so that it has more energy inside of it. So you have to think about the problem backward now for the ice versus that of the hot cup of coffee. Now, how much temperature will actually increase? Let's say, for example, I put something on the furnace and turn it for about 5 minutes. Depends on what I put there. If it's water, its temperature probably will increase by this much. If it's a spoon, for example, its temperature will increase by this much. If it's a different substance, for example, a spoon made out of metal, that is. If it's a different metal, granted that it doesn't melt or burn, it's going to be with this much. So as long as there is no phase transition, as long as I don't go from liquid to gas or some other transition, then the gains and the losses, they depend on the material you put in there. And that is what is known as the specific heat. Every element can absorb so much heat before its temperature increases. So this is a property of the elements, just like their masses and other things, like their densities, I should say. This is specific property for every material. And finally, we're going to talk about thermal expansion. Thermal expansion, you take a metal, like for example the spoon, and you put it on the iron. No, spoon is a bad example. You have to have it as long as possible. I mean, to have it linear form, to see it appreciably. And fix it from one end, for example, and heat it. It's going to expand. It's going to be longer. Now, if you put it next to ice, it's going to contract. Okay? It's going to shrink. So contraction and expansion depends on the material itself, too. And it depends on the length of the object. The longer it is, the longer it's going to get with the same temperature. So that's something that we have to take into account. I know for some of you today who are doing physics 11, we have lab experiment on this very same relationship. So the math relationship is the expansion, how much change in length, delta L, is related to the initial length, namely L naught, times the difference in temperature. If you put a lot of temperature gradient for it, it's going to expand longer. And every material has its own, basically, own coefficient of expansion. So now iron is different than aluminum, different than other materials. So this is specific to each and every one of the materials with heat. And that's what you see actually when you're driving, for example, and you notice that, or actually when you go to next to the train tracks, they come in different basically portions. And between each and every portion, there is a gap. And that gap is just to allow them so that when they expand, they don't buckle. There is room for expansion, okay? And same thing in the freeway, it's divided, for example, in different sections, so that when in the summer they get longer, so that they don't buckle. There is room for them to expand, and in the winter they contract. And the same thing what you see, for example, in the power lines and the telephone lines. I don't think that they do telephone lines anymore, but the power lines, you see them basically sagging, and that is because, again, so that in the winter they are actually contract, and the summer they sag even further. If you do them straight out, then in the summer they try to expand, and I'm sorry. If you do them in the summer like this, then in the winter they try to contract, and in doing so they will snap. So that's basically something that, as an engineer, if you're trying to build things, you have to be aware of. Temperature plays a major role. So, for example, if you are building a building and you need a beam of steel to be part of it, you have to account for the fact that the steel will expand with the heat and contract with cold. So you have to be aware of that. And when you build that, you have to do the calculation correctly so that the building doesn't start to deform and basically come apart. Again, all of this is part of the processes of heat. Okay, all of it has to do with temperature. So the key word in here, that is the discussion for this afternoon. One of the things is temperature and heat are not the same. Temperature has to do with the internal energy of the substance, whereas heat is the exchange of that energy. Exchange of energy due to the difference in temperature. Okay? So if there is a temperature difference, one object is hotter than the other, and they need to exchange energy, they use heat for it. And it's measured in joule, it's an energy, okay? Whereas temperature is a measurement of how much energy actually the system is, how fast it's moving. The hotter it is, the faster it's going to move inside. Okay, so this is the introduction for the topic. So again, temperature is a number that corresponds to the warmth or coldness of an object. So you need a number for it. You need to measure it, okay? Intuitively, we have that notion, but intuition is not good enough. We really have to have numbers for it. Measured by thermometer is a per particle property, no upper limit to the temperature can be as high as it can be. For example, inside the core of the sun right now, it's several million degrees. I mean, actually, I think it's about 20 million degrees inside the core of the sun. So it can be very hot. And it's hotter even on some other stars that are bigger. So it can be very, very hot, very high. But there is definitely a lower limit for it. In the famous experiment involving gases with specific densities, people noticed the following. As the temperature, this is the old scale, the Celsius scale, 0 degrees Celsius, okay? That's a valid scale too, it's used today too. And this is, for example, the pressure of a gas, okay? So what happened in this case is, or the volume, it doesn't matter. Let's take the volume or the pressure, okay? One of them. If you increase the temperature and keep the pressure constant, the volume increases. And it increases linearly, okay? From 0. If you decrease the temperature below 0, it's going to decrease further. But there were limitations at that time into how far you can go with temperature. You didn't have a lot of equipment to do it. Now, if you take a different material with different properties, it's going to do something similar, okay? But a different slope, basically. If you take different material, basically with the different properties, it's going to do something similar. But the slopes in here are not necessarily the same. What they have done is extrapolate these numbers to what happened if somehow the volume goes to 0. This meets in here with the x-axis. This meets in the same point in the x-axis, and this meets on the same points in the x-axis, negative 273 degrees Celsius. At negative 273 degrees Celsius, at constant pressure, the volume seems to have gone to 0. Doesn't make sense, does it? It's impossible. There is no such a thing. Or at constant volume, the pressure drops to 0. It doesn't make sense too. That's why this limit is a theoretical limit. It exists, but we can never reach it in laboratory. Okay? So there is a lower limit for temperature. So people, what they did is, instead of using the centigrade to measure the temperatures, they came up with a new unit for measuring temperature, and that is the Kelvin. So Kelvin, 0 Kelvin, is negative 273 degrees Celsius. So there is a conversion factor between Kelvin and Celsius, and the relationship is very simple. Kelvin is simply Celsius minus 273 degrees. Sorry, did I say minus? Plus, because I have to shift it this way. Okay. In other words, at 0 degrees Celsius, where the water freezes, it's 273 degree Kelvin. Room temperature, where we are normally account for, is about 300 Kelvin. So this is basically the unit that we use. The reason why I'm mentioning that is because at some point we're going to talk about PV equal to nRT, which is an important relationship for gases. And this is the law that we're talking about, actually. This temperature is not measured in degrees Celsius. This temperature is not also measured in Fahrenheit. It's measured in Kelvin. Another thing that is also usually asked about is the degree. The word degree is when we say Kelvin. I mean, when we say centigrade, we say degree Celsius. When we say, for example, Fahrenheit, we say degree Fahrenheit. There is another unit also, what is it, the Rankine or whatever. So we also use degrees for it. I'm sorry, that's probably... The Kelvin is the official unit, and you don't have a degree associated for it. That's the only thing I want you to be aware of. And this is the temperature used by scientists. This is the one that comes in this law and every law that you see in thermodynamics, okay, or any time temperature is involved, okay. At that point, when temperature is 0 Kelvin, that is exactly the lower limit that they are talking about in here. So this was discovered experimentally. You cannot go below that temperature. There is no way. At that point, the pressure will become negative, which doesn't make sense at all. Okay. Even pressure equal to zero doesn't make sense. As a matter of fact, at that point, if it's possible, the quantum effect will take away and prevent you from even reaching 0 Kelvin, let alone go below it. So that's basically the answer to that question, why we cannot go beyond below that. Okay. So temperature is proportional to the average translational kinetic energy per particle in a substance. And this discovery was due to Mr. Actually, first of all, this was experimented with. Okay, we were doing experiments like the one, for example, PV equal to an RT and things like that. Then Mr. Boltzmann, in the late 1880s, in the late 1800s, basically, he came up with an explanation, and it has to do with the kinetic energy of translation for particles in the room, basically in a box, and he found PV equal to an RT using that way. All he used actually is the same thing that we talked about from day one, F equals to ma. That's all you need for it. That's all he needed. Okay. He didn't use actually exactly F equals to ma, but he used the energy, which is 1/2 of mv squared. That's one thing. And also he used the fact that in an elastic collision, the momentum is conserved, P equal to mv. So he used the change in momentum is equal to the force, and that's basically how he used it. So he didn't use it in this form, but he used it in with the momentum. So in other words, since the momentum is derived from this expression, that is the expression that he relied on. So just to show you how that thing that we discovered a long time ago can explain a lot of things. The only difference is that this is an average thing, and since we cannot do everything, we cannot calculate every single particle in the room. So basically, we come up with averages, and that's how temperature is. So temperature has to do with the kinetic translation of the particles in the air. For example, this room I'm sitting in, it's made up mainly of nitrogen and oxygen. That is the air, and those particles are moving. The faster they move, the hotter the room is going to get. The same thing for wherever you are right now. Gas is how fast the gas particles are bouncing to and fro. Okay. Liquid, how fast particles slide and jiggle. Okay. And solid, the same thing, how fast particles move as they vibrate. So again, all of this has to do with motion. That's why when you reach 0 degree Kelvin, they should freeze. There should be no motion at that point. But I mentioned quantum mechanics because no matter what happened, there is actually that finite motion that prevents it from reaching that 0 Kelvin. Okay. Again, thermometer, and I already mentioned the fact that how it was allowed, how we are allowed to do such a thing, and that is because of the zeroth law that says basically, if system A is in equilibrium with system B, and system A is also equilibrium with system C, therefore system C and system B are also in thermal equilibrium, which allowed me then to make out of system A thermometer and make it in equilibrium with a standard material like, for example, water, and then compare that thermometer now in any other substance to measure its own temperature. Okay. Again, you can use mercury or alcohol because you would want it to really see the changes in it. Put the thermometer made out of mercury, for example, in frozen water, and then put it under a heat and see how the mercury starts to rise, and scale that accordingly. Again, reading occurs when the thermometer and the object reach thermal equilibrium. It's very critical that you need to have a thermal equilibrium. The infrared use a different principle, and the principle is actually the Wien's law, which we're going to discover later on. And that is basically has to do with the radiation. Okay, so that's a different kind of thermometers. Here is the scale thermometers. Okay, we have the Celsius scale. 0 degrees Celsius is when water freezes, 100 degrees Celsius when it boils. So here is your 0 degrees Celsius, and here where it boils. Usually it's not practical for too low temperatures, and it's not practical also for very high temperatures. So it's really not that practical. Okay, unless you use a different kind of gas in there, so then it's a different material in there, then you can go for lower temperatures. The Fahrenheit, it freezes at 32 degrees, and boils at 212. It's the same temperature, by the way. 212 and 100 degrees, they are the same temperature. They mean the same thing, but on different scales, okay? Kelvin scale, this is the one. Notice the little zero on top of the units in here. This one does not. So when you're talking about Kelvin, you don't append to it a degree. So 0 Kelvin for freezing point and 373 for a boiling. Because remember, it's 0 Kelvin. Wait a minute, 0 Kelvin for a freezing point. That's wrong. 273. Can you guys correct this? This is the second point that you need to make sure that this is the second point of the discussion. Water does not freeze at 0 Kelvin. It freezes at 273 Kelvin. Go a few slides back. So this is 0 degrees Celsius, but it's actually 273 because, can you guys make that correction, please? Everybody? And this is the second point of the discussion because we want to fix that. So water does not freeze at 0 Kelvin. That is a no-no. Okay? I didn't understand, Isaac. Okay, no better. Thank you. So the idea here is this is wrong. Please correct that. This is nonsense. The water does not freeze at 0 Kelvin. It freezes at 273 Kelvin. K. Okay? Not 0 degree. 0 at absolute 0, same size, degrees. What is 0 at absolute 0? I don't know what that is. Yeah, it is 0 at absolute 0, basically, which is really something that doesn't exist. And like I said, it's not practical to have that number. Jeffrey, were you going to say something?
You're saying it freezes at 273?
Water freezes at 273, yes, Kelvin.
Okay, not 0. Okay.
Not 0 Kelvin. That is not correct, okay? Please correct that. Thank you. The scale, of course, is the same because it's only a shift, okay? A Kelvin is the temperature, whatever it is in Celsius, plus 273. So if water freezes at 0 degrees Celsius, it must freeze at 273 Kelvin, basically, okay? That's the point in here. So you add to it this many degrees, and now the whole thing becomes in Kelvin. Now, if you take a difference between 2 Kelvins, basically 2 Kelvin readings of temperature, it's the same difference between them in degrees Celsius. That's why sometimes some laws that involve the difference in temperature, like the one we're going to do for the linear expansion, that you can measure it in Kelvin or in Celsius. The one that I mentioned earlier, the change in the length of a rod, subject to a difference in temperature, difference to its properties alpha, times its initial length, times the change in temperature. This temperature, because we're talking in change, doesn't care if you're using Kelvin or using Fahrenheit. It's the same thing. Kelvin or Celsius. It matters if you're using Fahrenheit. Don't use Fahrenheit, okay? Do not use Fahrenheit. That is for that law. So if you guys are sitting in here and you're going to do the experiment later on for physics 11, don't use Fahrenheit. Use centigrade. That's fine, and Kelvin is fine, but not Fahrenheit. Okay, that is important. There is another law that we will see shortly for the heat, and also the heat and the specific heat, and that too has a delta T in it, the change in temperature. So the amount of heat a substance will receive, we will see, it has to do with the mass. How much mass you have, the more water, the more heat you need to boil it. If you have less water, you don't need as much heat to boil it. So that's one thing. To bring its temperature from whatever it is to 100, basically. That's what means boiling it. Times a property, which is the actual specific heat that we're going to be talking about, times the change in temperature. In that one, too, you could use the temperature whether you're in Celsius or Kelvin. Do not use Fahrenheit. Now, another law that I wrote earlier today was PV equal to nRT. That you don't have a choice at all. That has to be in Kelvin. That's why, as a safe bet, use Kelvin all the time. That way, all of your bases are covered. Okay? Use this expression. Convert everything to Kelvin so that you're safe. Again, for this two, you don't have to. For this guy, you have to convert to Kelvin. Okay? That's why physicists usually try to first do the conversion and be done with it. Okay? So at the end, you have the answer and you're done with it. But sometimes it's a waste, like in these two expressions, you're adding 273, but you're subtracting it, so it might lead some confusion, so that's fine. But do not use Kelvin and Fahrenheit in any of this, all of them, okay? Unless you buy something from Home Depot that is rated in, I don't know, BTUs, and everything has this, the American system in it, the so-called standard system, then probably you have to use the Fahrenheit to find out exactly the thickness that you need to do in order to isolate the room or to make it more warm or something like that. So if you go to Walmart, then you're okay. Then you can use the Fahrenheit for your measurements, and you can tell him in Fahrenheit or her in Fahrenheit so that they can give you the right thing. Okay, I want to make this room between, I want to keep it between 73 and 83, then they know what you're talking about and they give you the right thing. But if you are in this class, no. Or actually, any place in here, so no. Okay.
I had a question.
Yes.
Oh God. What what is all that all divided by, like the C? Is that C plus 273 divided by what's on the bottom? I can't really tell
There is
anymore.
no divided. That's just a
Oh,
box.
sorry.
There's
And
no
what's on the
divided.
right?
Okay, hold on. Let me write it down in a clean fashion. Okay. Let me
Thank
get
you.
a pointer in here. And I don't want you guys to be confused about that. So the conversion expression is, let me type somewhere in here. Can I type in here instead? And let me make the characters a lot bigger than this because 11 is going to be too small. Let's make it 28. So Kelvin is whatever the temperature is in degrees Celsius, okay? So if, for example, room temperature is 20 degrees Celsius, add to it 273, period. So this now answer this temperature. So if you like, this temperature now is in Kelvin, and this temperature now is in Celsius. So this whole thing becomes basically the expression. If you are math inclined and you would want to use an expression, that is basically how this thing look like. Okay? That is the expression. Now, if we're going to use later on the change in what is it? The change. Oh man, why is it so tiny? Did you guys see that thing there? It's so small. Okay, the change in length must be equal to, again, let me get this thing out of the way. Must be equal to the coefficient, because different material they expand at different rates. Okay, so some of them will have, and that is expressed in terms of alpha. Everybody calls it alpha, so we're going to call it alpha in here too. Times the initial length also, which is important, times the change in temperature, and the change in temperature is expressed by this expression. Here is what I'm saying in this expression. You don't have to use uh, Kelvin. You can still live with centigrade, okay? But you cannot use Fahrenheit. That is the only thing. Again, there is another expression that we will see later on for the specific heat. The specific heat is related for the mass of the object times the its own specific heat times. So also this expression, you can use centigrade. You can use Kelvin, but you cannot use Fahrenheit. So that's basically the three expressions that I was showing there. I don't know that the slide became too much things in there. Yes, Kyle, that's exactly how you have it, okay? Thank you. So This slide now became a mess. But I myself, if I see it probably 3 days from now, I have no idea what I wrote in here. Okay, unless I see the recording again. Okay. So there is twice as much molecular kinetic energy in 2 liters of boiling water as is in 1 liter of boiling water, which will be the same for both. Okay. So here is the trick. You have to understand it in here. You have two, oops. Did I, yeah. You have 2 liters. Okay. You have 1 liter and 1 liter. And you have twice the kinetic energy. Okay. Twice the energy actually. 2 times U. The symbol for that is U. Okay. And now you have 1 liter, but it is 1 U. Okay. This twice U, this molecules must be moving with this much speeds in order to account for this energy. Okay. But they're everywhere now, both parts of the liquid. They must also be moving with the same speed now here to maintain that 1 U, basically, when you separate them. So what is true then, since how fast they move, is their energy. So basically, if you take 2U now and divide it by 2 liters, each liter will take with it 1U. So the temperature is the same, because how fast they're moving is the temperature. So the temperature of both of them must be the same. This has more thermal energy in it than this one, because it's twice the energy. So you cannot tell me, in other words, if you want to use this one, that's why the ocean, when they get warm, they warm their entire environment because they have more heat in them. Okay. When they're cold, they cool the entire environment next to them because they have less heat in them. So they try to grab it from everybody else next to them. To say that a body has a higher temperature than a body B is to say that body A has more. It has to be internal energy in this case. Oh, I'm sorry. Yeah, internal energy, yes. Did I say? No, I'm sorry. That's nonsense what I was saying in here. You can have 1 liter of water and you can have 10 liters of water, okay? And this is 1 liter. This is sitting, for example, as a temperature, let's, for the sake of argument, make it 22 degrees, okay? And this is sitting at 20 degrees Celsius. So definitely this liter has more temperature than this 20 liters by 2 degrees. But then, in terms of internal energy, this has more stuff of it. So this has more internal energy than this one, okay? So what the temperature is the kinetic energy per particle. So this particles are moving faster than this ones. So the correct answer is C now. Does this make sense to you guys? Albeit, this is harder. This still has more internal energy than this one because you have more stuff of this one. And the gradient in temperature is not that much.
So because the 1 liter container is smaller, the water particles move more? I'm not getting it.
You put it under a heat sink. You put it, for example, under a boiler, okay? And he brought it his temperature and read it with thermometer, and it says 22 degrees Celsius. Okay, it's hotter. You could do that. 1 liter, put it in what is it put it in the pot, in a pot or whatever you want to use.
Yeah, like on the stove top.
Yeah, and put it on the stove and monitor its temperature with a thermometer, and the thermometer says now it's 22 degrees. Whereas the bucket next to it has 10 liters in it, and you put the thermometer in there, and it tells you that it's only 20 degrees. So definitely, the particles in this one are moving faster than the other one, okay? Because of the higher temperature. But if you're curious, trying to see which one has more internal energy, of course, definitely the 10 liters in this case has. Obviously, if both of them have the same temperature, the 10th liter still win.
So the
Now,
10 liter would have more kinetic energy if they were at the same temperature?
more internal energy, yes, because it has more stuff, more water. Okay. Now, if the gradient in temperature, and this is key in here, if the difference, if this one is, let's say, for example, 100 degrees Celsius, it's already boiling, okay? This could potentially end up with more internal energy than this one. So it's not just the quantity of matter that matters, it's also the temperature. So the combination of both is what makes up the internal energy of the system, okay? So the question in here, since it's difference in temperature, that's what the question says in here. System A has higher temperature than system B. Then in this case, on average, it has a higher kinetic energy per particle, because that's what the temperature measures. Sometimes when I'm in the full new moon. Okay, yes. Did anybody take thermodynamics or did stuff like this one in chemistry? No? Okay, heat isn't, okay, this is not wrong. Okay, that's, I'm sorry, it's wrong. It's transfer. The key word here is transfer. Okay. So it's really energy in transition between two things. That's what heat is. Okay. So you have to have two things in order to talk heat. Heat is somewhere in here. That is where Q is. Okay. When you put your hand on a cold cup, you feel it cold because heat is leaving your hand toward the cup and it's making it warm. So your hand now detects that heat is being extracted from it. So it feels colder. When you put your hand, for example, on a hot cup of coffee, you feel it warm because heat is actually coming from the coffee to your body. And the tiny particles that makes up the skin of your hand starts to move faster and faster. And that is how you feel heat in that case. Okay. Whereas if you touch something cold, they start to move slower and slower, and your sensory system tells you this is colder. Okay. So that's the thing. The heat itself is that thing that you're exchanging between the two. The energy that is moving from the hotter one to the colder one. Okay? So it's an internal energy in transit. So you catch it in between. That's where heat is. So a substance does not really have heat, it has temperature. It only exchanges heat with it's somebody else. Okay? So heat is something in between them. And it's an energy. The units for it are still joules, J. Flow of internal energy from high temperature substance to a low temperature substance until thermal equilibrium. This is the natural flow of things. This is the second law of thermodynamics. Okay, I know we didn't talk about the first law of thermodynamics since we talk about the first law, the second law. In this case, if an object, this is what the first law is talking about. Let me tell you what that is. Let's say, for example, I have an object that has an internal energy. Okay, that object can do two things: to either gain energy or lose energy. And those two things are either receive heat, you put it, for example, under a heat sink, and that will raise its temperature. Okay? Which means its internal energy is higher and higher because it received heat from the hot source. Or you put it in contact with a cold source, and then it's going to lose heat to that. So it's going to gain heat or lose heat. I'm sorry, it's going to gain energy or lose internal energy in the form of heat that way. There is another way of doing it without even having heat involved, and that is by having it to do work. Okay? When the gas expands, for example, it does so by doing work against the environment. And you can maintain it in a blanket if you wish. Wrap it around the blanket in the thermostat. Not thermostat, what do you call it? The thermos. Put it inside the thermos so that it doesn't give heat or take heat. Okay? And it still, in that case, loses energy because it's expanded. So there are two ways for it. So what the second law, what the first law of thermodynamics tells you is that an object internal energy, the change in its internal energy is that of how much heat it gains and how much work it does. That's basically what the first law of thermodynamics says. Which brings us to the second law of thermodynamics, which is this one. Okay, this is the one that is actually also called the law of entropy at some places too. Okay, So internal energy never flows as unassisted from low temperatures to a high temperatures. That it's still the same thing, unassisted. I mean, you tell me, okay, how about the refrigerator? I tell you, okay, the refrigerator is actually assisted. Because think about it. You take something very cold, it transfers through Kyle, to answer your question, heat transfers actually through a vacuum using radiation. The only reason why the Earth is hot today, for example, and yesterday and the day before, was the heat received from the sun. Okay, and that heat came through vacuum, so it did not struggle. So it comes through radiation. So there is ways for it to go through vacuum. Okay, so heat can move, but it has to move through different forms in that case. Okay, so I should say energy. It's not necessarily heat, but when it comes to Earth, it becomes heat. Okay, what we call heat, because the temperature rises and then it's exchanged in the form of heat. So I was a little bit kind of I did not really answer that question correctly. Okay, so I lost my train of thoughts in here. We're trying to get into the. Okay, we'll come back some other time. So if a red hot thumbtack is immersed in warm water, the direction of heat flow. Yeah, I'm sorry. I was going to go back to the example of the refrigerator, which is a very important example. Because I mean, normally if I put my cup of coffee, or for example, if I put this cup right now, it has a cold water, my ice melted. If I put it and take it back and put it in the refrigerator, for example, in the freezer section of the refrigerator, it's going to get colder. It's cold and it's going to get colder. So what happened in this case? I'm extracting heat from a cold place to make it even colder. So what the refrigerator does in this case, it works backward. It pumps heat from a cold source. Let's say, for example, you put your meat in the refrigerator, it's cold already. Okay. Even when you put it 5 minutes after, it's colder than when you put it for first time in. And it's going to get colder and colder until it reaches the temperature you decide on the refrigerator, okay? You set it on the refrigerator. Once it reaches that temperature, it's not going to get any colder. So let's say, for example, the temperature right now, for example, okay, is 12 degrees Celsius, okay? And you set the refrigerator for it to reach temperature of 4 degrees Celsius, okay? Right now, when you put it after 10 minutes, for example, the temperature has dropped already to 10 degrees Celsius. What the refrigerator does in this case is going to take heat from it and make it colder. It's going to bring it down to 9 degrees Celsius. And that's not enough. It's going to take more heat from it and brings it down to 8 degrees Celsius, 7 degrees Celsius, 6 degrees Celsius, 5 degrees Celsius. At 4 degrees Celsius, it's going to stop taking heat from it because it has reached the setting of your refrigerator. So at that point, it's doing something that is not normal. So what is it taking that heat? It's dumping it in the environment. As a matter of fact, just go behind the refrigerator, you see that it's very hot. Okay? So it's taking heat from something that is very cold and dumping it in the kitchen that is hotter than the meat that you put in there. But that is assisted. How do you know? Watch the bill for the end of the month. There is a motor there. There is actually a pump there. Okay? That circulated gas, and that gas basically is compressed so that when it goes, it's going to expand next to the inside the refrigerator environment. In doing so, it's going to extract more heat in order for it to expand and dump it outside when it expands again more to basically dump the heat to the environment and go back through the compressor, and the compressor will circulate basically each cycle taking more heat from the stuff that is inside your refrigerator and dumping it outside. And if you don't believe me, yes, it feels cool in front of the refrigerator, but just go behind it and you will see how hot it gets there. So that is the principle of the refrigerator. So it's not an unassisted, it is assisted there. So you can do this process and it is assisted, it's helped on the refrigerator or the AC unit, it's the same thing, okay? You have to help it to do that, but not on its own. On its own, it's the other way around. Take that meat and put it outside in a hot day, and you will see after a while what happened to it. You would not even dare to come close from it, okay? Don't do this experiment, okay, unless you have some meat to waste. So if a red hot thumbtack is immersed in warm water, the direction of heat flow will be from red hot. So the heat is going to go from, somebody answered it. Let's see here what B says. Yes, from the hotter to the colder, in this case, the warm water, albeit it's warm. Okay, that is actually the second law of thermodynamics we've been talking about in here. Mr. Joule did an experiment. What time is it? Oh man, it's 5:05 already, and we are not even halfway. Probably have to finish this topic later on. Anyway, we still have time. So Mr. Joule did an experiment basically because heat was a problem. Okay, and if you have ever heard of the word calorie, it's coming from basically the fluid that the people were talking about. They thought that heat actually was a fluid. Okay, they called it the calorific fluid because you can feel it actually that there is something flowing. Actually, you can visualize it that there may be substance in there. Mr. Joule did an experiment where he actually showed that if you take a liquid basically and you put basically he put flaps in them and put mass and he dropped the mass and he saw the potential energy lost by the mass equates to a change in temperature of that fluid, and the change in temperature has to do with how much heat it is through this relationship actually for water through this expression or any substance. Okay, so if you put a thermometer in it, you find how much change in temperature it is, how high the temperature is going to go. You know the mass of the substance, it's water, for example. You know the specific heat of the water, so you can find how much heat it is. So he was able to calculate the heat just using the thermometer. At the same time, he knows how much energy it went in it because he knows how high the mass dropped on the other side. And from there, he was able to tell us that 1 calorie is 4.18 joules. Okay? 1 calorie is 4.18 joules. Word of caution, there is a big distinction between a calorie and a calorie. Okay? One capital C calorie is 1,000 little c calories. Okay, here is another task for the day today. If you go and check on all of your, let me try to find something in here, a picture that I have made a long time ago, if I can find it. If you go to your food, the food, for example, in your house, okay, chips, whatever you have at home, okay, you will see them labeled basically with let me see this picture. No, you will see them labeled. No, not here. I'm looking for a specific picture I took the other day. No. Okay, so you see them labeled with calories. How many calories there are? Remember when you go, for example, to a restaurant or you go somewhere in the store shopping, they tell you how many calories. They're required to actually write it with capital C because it is capital C. It's thousands of calories. So if they tell you this, for example, has 270 calories, it's capital C. That's 270,000 calories. And each calorie is 4.18 joules. So imagine yourself having some chips, for example, and the chips overall, they have this many calories. So if it's 270 calories, that is actually 270,000 big little calories, and each one of them is multiplied by 4.18 joules. So you have 4.18 times 270 times 1,000. That is how many joules really you have taken. Okay, I don't think Halloween is coming and some of you are tempted. You have to be very careful really with those things because they carry with them a lot of energy. If you were to calculate how many steps do I have to go up and down for me to burn those calories, you will find that you're going to go forever just for a single candy if you're going to rely on that. So the challenge for today is, that's another one. So we already have two of them already. Okay. The first one is a difference between heat and temperature. The second one was to make that correction. And the third one today is to go through your kitchen, the food that you have at home, find one item or more if you like, okay, and tell us how many calories in it. First of all, what the item is. Let me type it, okay, because I don't want you guys to forget these things, okay? I know some of you are going to watch this thing later, so probably need to pay attention to what we're saying at the same time. So you're going to tell us what the item is, number one. Number two is how many calories. It has to be on the label somewhere in there, okay? If you look at the label, it's going to be in big letters, okay? How many calories? And the second one in here, the last thing that you're going to tell us uh, is it properly spelled? Okay. What I mean by it is capital C. Some of them, what they do trying to circumvent this, they make everything in caps, the whole thing in caps, okay? So that you're a little bit confused, thinking that maybe if I put things in lowercase, I have less calories, okay? But it's still, they have passed the test. Those who are honest enough, or at least they don't care, they put with a capital C and they move on. If somebody had put it with a lowercase c, they have made a mistake, and you really have to send them a letter telling them, hey, do you really mean that this is how many calories in it? Only 270 lowercase c calories, basically? If they have spelled it correctly, then they pass the test. They are fine. Okay, so do you guys understand? So you're going to find an item in your kitchen or from the shopping or whatever your favorite thing is. And I'm going to do the same thing, by the way. I'm going to post one of the for you guys. And you're going to basically tell us what is the item, okay? How many calories it has, and is it properly spelled? Now, the last part of the thing in here, were you surprised really to think that this is that high? Because remember, each one of them, you have to multiply it by 4.18 times the number that you have times 1,000 to find how many joules to have it in joules. So it's going to be a lot of energy, okay? And then were you surprised? You can pick up an item from Halloween stuff, okay? Were you surprised? Yes, that's the Samantha is saying, I'm looking for a capital C. Yes, that's what you're exactly looking for. If it's lowercase c, you have to be surprised, okay? At that point, it's really a problem. You may have to contact the person who made that product and tell them, do you really mean this is how much it is? Because this is too low, okay? And then the last part of the task is you're going to check if you are surprised that it has that many energy, and would you make any changes in your diet? Okay, it's going to be a lot of energy. One of the experiments we do for physics 11, if we were doing it actually in class, is we bring actually Doritos and we burn them, put them on under the basically as they catch fire, and we put it on basically what is the flax in here, where we put the flask, I should say, where we put the put water, a thermometer in it, and we watch the temperature rise. And based on how much the temperature rises, we'll determine how many calories into that Doritos were. So it's a fun experiment if we were alive to do it. Of course, don't do this at home because it involves fire, and that's not as safe as. So usually when we do it in the lab, we have a safety there, and the whole thing, and there is where the smoke escapes and things like that. So that's how you determine actually how many calories in food is. So you burn it, and you see how much energy you deliver. Okay, how much energy you get from it. And you'll be surprised. There's a lot of calories in almost everything we take, especially the Halloween stuff. Okay, Halloween things will have a lot of things in them, and I'm not discouraging you from celebrating Halloween, but you will be surprised into all of those things how much energy they pack in them. Okay, I don't think that we have enough time today to finish the rest of the stuff. We are in slide 15. We are almost midway. in terms of everything that we need to do. So we're going to finish this one after the exam. And I already mentioned a few things related to the lab. The thing that is going to be critical for the lab this afternoon is delta L is proportional to delta T. Okay, that's what we'll be doing. And the change, delta is a change. The change in the length of a rod is proportional to the change in temperature. Okay, so that is needed for this afternoon. And when we meet at 6 p.m., actually, we'll go in detail about this point in here. And we will see and we will measure that, and we should be able to have no we should be able to do that in the lab, okay? There is another activity for you guys too, for physics 11, and that is to take two objects, and you guys from physics 10 who are not sitting in that class, you can do that too, and it's fun too. What you can do is pick up two objects in your kitchen, namely, for example, a wooden spoon and a metal spoon, and put them next to one another. They don't necessarily have to be touching, just next to one another, and wait a long time, so that they both will be in thermal equilibrium with the room that they are in, the kitchen basically. And then put your finger on both of them and see which one feels cooler, I should say. And you will be surprised that one of them will feel cooler than the other. But the question, are they really different in temperature? They must have the same temperature because they have been sitting next to one another for a long time. But surprisingly, one of them feels cooler. That's why if you are, for example, on a very cold day and you go, for example, in the bus and there's those benches that are in the bus, and if it's made out of, for example, aluminum, and you sit on it, it feels very cold. Vice versa, if it's a very hot day and you sit on the aluminum, it's going to feel very hot. Versus, for example, if it's a wooden bench, that you don't feel the same thing. So it feels better in the hot day and it feels better in the cold day because it doesn't have that much. But they have the same temperature. They must have because they're in thermal equilibrium with the kitchen. So what are we talking about then? What's going on then? But that's not part of your task. You're not required to do this for physics 10 unless you're sitting in physics 11, which is actually going to be part of your lab. Okay, I'm going to see you guys for those on physics 11 in about 40 minutes, I should say. The others, don't forget you have everybody that you have an exam on Tuesday. So there is no class on Tuesday. The next time we will meet in class is going to be Thursday, a week from today. Any questions? If you guys don't have any questions, I'm going to stop the recording and I'll see you later.